Now let us discuss the swing equation. What is this swing equation? So we will not derive the entire swing equation. We will just start with one equation, which is m into d square delta by dt square. This is delta m, which is equal to PA, which is in turn equal to PM minus PE. So I will tell you what are the meanings of each of these parameters. This is one form, and another way is 2GH by omega Sm d square delta m by dt square is equal to PA, which is PM minus PE. First we will discuss about delta m. This is the load or the torque angle. Now we know that synchronous machines, they rotate at what? Synchronous speed, right? This we are taking as omega Sm, right? Here in the equation you have omega Sm, that is the synchronous speed. Now what will be the units here? It will be in radians per second, okay? And further we are going to write as mechanical radians per second to differentiate from electrical radians per second, which we will discuss shortly, okay? So this is the units. Similarly, the units of delta m, what will it be? It is mechanical radians. Now what is delta m, the load angle or the torque angle? It is the displacement of the rotor axis from a synchronously rotating reference axis. So that means if you are taking this as the reference axis, this itself is moving at a synchronous speed, and the rotor, the machine rotor whatever we have, that is also rotating as at synchronous speed, but it is displaced from the reference axis by an angle delta m, okay? So this is the rotor axis, and what is the rotating velocity? It will be the synchronous speed. So basically the reference axis and the rotor axis, the relative velocity between them, that is 0, right? This is the synchronously rotating reference axis here, okay? So with respect to this synchronously rotating reference axis, the rotor axis is at an angular displacement of delta m. But what is the actual angular displacement? The actual angular displacement, this will be with respect to some stationary reference axis, right? This we represent as theta m, okay? So this will be related to the load angle as omega Sm into t, right? The speed into time will give you the angular displacement plus the already existing displacement delta m, okay? So here we have delta m, this is omega Sm, and here we have theta m, which is the actual angular displacement. Next, what is there? T is anyways the time, okay, with respect to time, and G here is the machine rating, okay? So G is the machine rating in MVA, megavolt ampere, okay? Next we have H, this is the inertia constant of the machine, okay? So this is equal to, H is equal to the stored kinetic energy in megajoules at synchronous speed divided by the machine rating in MVA, that is the megavolt ampere, okay? So what will be the kinetic energy? This is given by half J omega Sm whole square, okay? This is the kinetic energy divided by machine rating is G, right? We have taken the MVA rating as G. Now what is J here? J is moment of inertia, okay? So don't get confused, H is the inertia constant, whereas J is the moment of inertia of the rotor, right? Of rotor, and omega Sm is anyways the synchronous speed in mechanical radians per second, okay? Further, this can also be written as or half m omega Sm, okay? So half m omega sm is also one way in which you can express the kinetic energy divided by g. Now what is m here? M is the angular momentum. So this is related to the moment of inertia as m is equal to j omega. Next, what is left out? Here we have discussed delta m, g, h, omega sm. So we need to see what is PA, PM and PE. So these are the powers. Okay. First we will see what is PA. This is the accelerating power. And PM is the mechanical power. And finally PE is the electromagnetic power. So what happens in a synchronous generator? The mechanical input is given to the synchronous generator and it will give an electrical output, right? So that mechanical power input is this PM, okay? And whatever it is giving as the output, that is the electromagnetic power that is developed in the machine, right? So that is PE. So that is why for a generator, right, we write PA is equal to PM minus PE. So for generator, the accelerating power is nothing but the input minus the output. So if you take for a motor, it is going to be just reversed, PE minus PM. Now in power systems, we usually like to express in terms of the per unit system, right? Per unit system has its advantages. So we would like to express in per unit. Now the swing equation also we will try to do the same. This is the swing equation that we discussed before. dt square, this is equal to PA, which is PM minus PE. Now what is a per unit value? It is equal to the actual value divided by the base value. Okay. So this entire equation, if you divide by the base value, then you're going to get the per unit values of this power, right? Now G is the base value. It is the machine rating in MVA, and rating is usually taken as the base value. So what will happen if you divide the entire equation by G? Okay, then you're going to get 2h by omega sm d square delta m by dt square is equal to the accelerating power in per unit, and this is equal to PM in per unit minus PE in per unit. Now further, this omega sm, it is the synchronous speed in mechanical radians per second. Similarly, delta m is the load angle in mechanical radians. Now we wish to express in the electrical radians. So first we will understand what is the difference between these two. Okay. Now if you take a cylindrical rotor like this, okay, often you will have a salient pole rotor, but we are taking a cylindrical rotor just for the sake of understanding the difference between the mechanical and electrical radians. Okay. We will take the magnetic poles. This is the north pole, south, north and south pole. Okay. So this is how the poles will be present on the rotor. This is a 4-pole machine. Similarly, you can take a 2-pole machine. Okay. In 2-pole machine, you are going to have only 2 poles. One will be the north pole and one will be the south pole. So first we will consider the 2-pole machine. What is going to happen if this point we will take as point A. Now what will happen in one full rotation in 360 degrees? This point A, it will move like this and then come back to the same position. Okay. Now that is 360 degrees in mechanical terms. In electrical terms, what will happen? If this point has come from north pole to south pole, it is 1/2 rotation, and then again from south pole to north pole, it is 1 full rotation, right? So here there is no difference between mechanical and electrical radians. But now you see, if you see this 4-pole machine, what is going to happen here? Here north to south is 1/2 rotation in electrical terms, and from again south to north, it is a complete revolution. Okay. So here 360 degrees is getting completed in electrical terms, whereas the mechanical terms only half a rotation is being completed, right? So if you take the angular displacement in electrical terms as theta e, then this is what it is equal to 2 times the angle in mechanical terms, right? So when theta m is 180 degrees, theta is becoming 360 degrees. Now let us say it is a 6-pole machine. Then what is going to happen? Theta e will become 3 times theta m. Okay. So you are going to get the relationship as theta e is equal to p by 2 into theta m, where p is the number of poles. Okay. Now this is the angular displacement. The same goes for angular velocity. Okay. So if you take the angular velocity as omega e, and this will also be equal to p by 2 times omega m. Okay. So that is how the mechanical and electrical radiance, they are related to each other. Okay. Now what we want here, we have omega sm. Okay. The synchronous speed in mechanical radians per second. And here we have the load angle in mechanical radians. So we want to express in terms of the electrical radiance. Okay. So in electrical radiance, in electrical terms, the swing equation will become 2h by, instead of omega sm, we will write 2 by p omega s. Okay. Into d square, instead of delta m, we are going to write 2 by p delta by dt square. Okay. So here we are not using the subscript e, just normal terms we are writing. This is equal to pa, which is pm minus pe. These are all in per unit. Okay. So 2 by p and 2 by p is going to get cancelled. Finally, you are going to get the swing equation. This is the final form. Okay. So 2h by omega s into d square delta by dt square is equal to pa, which is in turn pm minus pe per unit. Okay. Further, this omega s you can express in terms of frequency as well. Okay. So what is omega s in terms of frequency? 2 pi f. F is the electrical frequency of the power, right? Electrical power frequency we can express instead of this omega s. Okay. So here you are going to get 2h by 2 pi f d square delta by dt square, which is pa, which is equal to pm minus pe in per unit. Here f is the electrical frequency and the unit is going to be hertz. Here you can see there is 2 in the numerator and denominator, right? So you can simply write as h by pi f. Okay. So this is the equation, swing equation. Now if you solve this equation, then what you are going to get? You are going to get delta in terms of the time. Okay. Solution of swing equation is delta as a function of time t. And if you plot a graph of delta versus t, that graph is called as the swing curve of the machine. Now at steady state, what is going to happen? This accelerating power is going to be simply 0. Okay. Next, swing equation of multi-machine system. So nothing different here. We have taken the machine MVA as the base MVA, right, in the previous derivation. Now what we have to do in a multi-machine system is we have to take a common MVA as the base MVA. Okay. So what was the equation? GH by pi f d square delta by dt square. This is equal to Pm minus Pe. We are talking about the actual values here. Okay. Now instead of dividing by the machine rating, so I will write here, this is the machine rating. and H also belongs to a particular machine, right? Now this entire equation, if you divide by the system MVA, then you are going to get the swing equation in the common base MVA. Okay, so that's the only difference. So here you also write down, just in case you forget it, G system is the common system base. Now swing equation of coherent and non-coherent machines. So we will understand first what is meant by coherent and non-coherent. So we saw that the delta versus T curve of a particular machine, that we call as a swing curve. Okay. Now two or more machines, they are said to be coherent if they swing together after a disturbance. Okay. Or in other words, their swing curves are the same. Okay. So you can write, when two or more machines swing together after disturbance, they are called coherent machines. So when these coherent machines, they are expressed on a common base MVA. Okay, the swing equation is going to look like this: H equivalent by pi f d square delta by dt square, which is equal to Pm equivalent minus Pe equivalent. Okay, so here what are these equivalent values? This is equal to H1 plus H2 plus so on till Hn. So here we are considering n machines that are coherent. Okay, for n number of machines swinging coherently, and this is the equation, and the H equivalent values is this, and Pm equivalent is also simply equal to the sum Pm of each of the machine, and Pe equivalent is also equal to the sum of each individual machine's electromagnetic power. This is n here. Okay, so you can also write here, they have the same swing curves. Now what is a non-coherent machine? They don't swing together, that means they are not coherent. So machines which do not swing together, or you can simply write, if they are not coherent, then they are non-coherent. Okay, are called non-coherent machines. So here the swing equation we will write for two machines only which are non-coherent. Okay, consider two non-coherent machines. Then the equation, swing equation, is going to be H equivalent by pi f d square delta 1 2 divided by dt square, which is equal to Pm 1 2 minus Pe 1 2. So here what is H equivalent? This is equal to H1 H2 by H1 plus H2. Delta 1 2 is delta 1 minus delta 2. This is the relative angular displacement between the two machines. And Pm12, this is the weighted mechanical power. This is given by Pm1 H2 minus Pm2 H1 divided by H1 plus H2. Okay. Similarly, Pe12 is the weighted electrical power. So this is given by PE1H2 minus PE2H1 divided by H1 plus H2. Okay, so this is for two non-coherent machines.